Okay, this is the final lecture of Math 331 for this semester, unless something catastrophic happens and the registrar finds out that we've missed too many classes or whatnot. So what I want to do is I want to build first on a nice solution we had yesterday to the expected value of the egg dark problem and talk a little bit more about expected values. This is one of the nice things about a class like this is you have some freedom in terms of what you want to cover. I know at least one of you has taken probability with me, and you may recall that one of my favorite theorems from that is the expected value of a sum is the sum of the expected values. So the reason this is so useful is it doesn't matter if things are independent or if things are dependent. Now, if you want to calculate something like variance, how much things are spread, all bets are off, and now dependencies matter. Which is not surprising, because if you look at, x plus y, if y equals x, or if y equals minus x, the variance is going to be very different in those cases. And if x is symmetric, then x and negative x will have the same distribution. If I look at x minus x, I know exactly what's going on. There's no variance. There's no uncertainty at all. So the big result in probability is what's called linearity of expectation. And what it basically says is if x1, xn are random variables with finite means, say mu I is the expected value of xi, then the expected value of the sum is just the sum of the expected values. And one of the nice things about doing this is this gives a quick opportunity to talk about probability. So, as one of my professors said, recall if you did not already know that by expected value of x, we mean the integral from minus infinity to infinity of x times the density function of x dx, if it's a continuous random variable, or maybe a sum of xi, and then the probability that you get xi if it's discrete. So this is just the average value. Anybody who has ever taken a class knows about the average value. If you are competitive, you know about the variance. If you went to Harvard, you know about the third and the fourth moments, about how spread out this is. I was visiting a friend, and they posted the first 4 moments of one of the pre-med classes so that the little Harvard freshman could know exactly how they compared to everyone. So most of us just look at the first 2. Variance of x is the expected value of x minus its expected value squared. And when you do some algebra, this turns out to be the same as the expected value of x squared minus the square of the expected value. And if you could commute operations of expectation and squaring interchanged, this would be 0. It turns out if your random variables are independent, then the expected value of a product is the product of the expected values, if they're independent. If they're not independent, this is false. It would basically tell you that everything has 0 variance, that there's only one possible value it could take on. Okay, so this is a phenomenal concept. This is why in a lot of problems, it's not so bad to figure out the average value, the average outcome. But to figure out what fluctuation, what window do we expect the answer to be around that is significantly harder. Okay, I'm just looking at the video, and it's fascinating. This little part where I erased over here, I can see as a huge smudge on the screen. All right. So what I want to do is there's various forms of this. I'll call this the movie line problem. So the movie line problem is the following. You have people waiting in a line to see a movie. We'll assume that there's one teller. And we will assume that all possible orderings of people are equally likely. Okay? And the question is, how many people, on average, do you expect the teller to be able to see? So what else might you want to assume to make this problem a little bit easier? You want to avoid a degeneracy. What could be one problem? So we'll assume the person's looking straight down.
So how many can they see?
Right, you want to know how many can they see. So you have a teller, n in a line, only see someone if taller than all before them. So what could cause problems? What could be a degeneracy? I'm sorry?
If you just have a bunch of children talker, you can't see anything.
With Shaq's in front of the line?
I'm sorry? Well, no, well, that's fine. If Shaq happens to be in front of the line, then we just see Shaq. What do you want to assume about the heights of the people? Distinct, right? What if you had a couple of people who were the same height? Then there could be some technical issues. So if necessary, you give people a slight hat or something, or give them, sneakers or high heels, something to change their height a little bit. Maybe Princess and the Pea, somebody wears 15 pairs of socks to give them that slight little extra boost. So let's assume all heights are distinct. And let's assume all orderings are equally likely. So let's let x, we'll call it maybe s of n will be our random variable, will be the number of people C with a given ordering. If you really want it to be formal, we have how many different orderings possible?
Many people factorial.
Right, so it'll be n factorial. So technically, I might apply, say, maybe Sn to a permutation. And you give me a permutation, Sn would tell me how many I see. So if you want to be really formal, maybe look at like Sn of sigma, where sigma is in a set of permutations of 1, 2, n, which has size n factorial. So I want to calculate, here's my question. What is the expected value of Sn? So one of the things we've hopefully learned throughout the semester is get weak bounds first. Can anybody give me any weak bounds?
1 or greater.
Yeah, it's got to be at least 1, right? No matter what, you're going to see the first person. So we know that 1 is less than or equal to the expected value of Sn. Anything else?
N factorial.
You can actually do better than n factorial. N,
Yes.
right? Right? There's only n people.
A bit better.
Okay, maybe unless maybe, or we didn't say what movie, maybe they're going to see The Sixth Sense. Oh, good, finally, I've made a movie reference people got. Only took most of the semester. All right, so maybe we see dead people, okay? Let's assume that we can only see the n people who are actually there, okay? So we know 1 is a lower bound, n is an upper bound. What would you guess? So again, I want to do guesses before we do anything. And when I say guess, I don't mean that you have to support your guess. I'm just saying, what's the thing to guess? N over 2. Or more generally, maybe some constant times n.
Constant times square root of n.
Okay, maybe some constant times square root of n. Well, as long as we're doing square root of n, what could we do? Or that's much lower, but we could do log n, and maybe constant times log n. But if we're doing square root of n, what should we allow as well? Yeah, any power. Maybe c n to the delta. Anything else as a possible guess? Yeah, constant. Maybe we just can't see that many people. And there's a wonderful problem called the marriage problem or the secretary problem. How many of you have heard of this? I'll send a link on this and I'll send a video. It's one of my favorite probability problems. Absolutely phenomenal in terms of what you can do. These seem to be natural guesses. So before we do the analysis, do you think it's closer to n over 2 or constant times n, or do you think it's closer to a constant? So you think it's closer to a constant. Why do you think it's closer to a constant?
I mean, my initial guess was that, if we assume that heights are random,
Right.
or if we assume that, there's a 50% chance that we'll see the person, that, we'll be able to see, there's 50% chance that, person X plus 1 is taller than person X.
Okay, so we have a 50% chance that the person is taller than the person in front of them.
And obviously, we can't really assume that because, if we keep on seeing people, then they're going to get pretty tall.
Right.
It's going to be less likely to see them. But then we're going to have, we're going to see the first person, and then we're going to have a 50% chance of seeing the second person.
Right.
We're going to have a 25% chance of seeing the third person.
Why 25% chance of seeing the third person?
Because there's a 50% chance that the second person. Oh.
So let's try to analyze this. So let's say we have 3 people. This would have been a great day for, Kayla to be here.
Never mind, man. I was thinking kind of like you see everyone up to.
So what's the probability you see the first person?
50 or
1, right? So probability we see. The probability we see the first person is 100%. What's the probability we see the second person? 50%, a half. What's the probability we see the third person?
It's harder now.
No, it's not.
If we assume the 50% thing.
Well, what you might be trying to do is maybe answering a harder question. What's the probability we see people's 1, 2, and 3?
Yeah.
I'm just asking what's the probability we see the third person. So
It's 1/2.
it's not 1/2.
Couldn't it be 1/4?
Okay, so I've got
The probability that they're taller than the.
I've got almost every fraction.
The probability that they're taller than the 2 people in front of them would be 1/2 times 1/2, right?
No, that would be. So the one possibility is it's 1/4. What are the other possibilities I'm getting? What else? 1/3. 1/2. Anything else? We at least agree it's not 1. Okay, good. There's a chance that we don't see them. So 1/4 is basically saying, look, we have a 50% chance of seeing this person, and then we need to be taller than the first person to see them. Or we need to be taller than the second person, and you have a 50% chance. But if this person is taller than the first person, does that influence our chance of seeing this person?
Yeah.
So they're not independent. What we're not trying to do is analyze the probability that we see all 3 people right now. I want to know what's the probability we see person 3. I don't care if I see people as 1 and 2. I just care, do I see person 3? So if I have 3 people, what's the probability that person 3 is the tallest of the 3? It would be 1/3. So this is the power of linearity of expectation. Is we're looking at it person by person. We're going to have an indicator variable. So let's let xi be 1 if c person I and 0 if don't. What is the probability we see person? Well, let's do person k. I like writing k's more than writing i's. What's the probability we see person k? 1/k. What's the probability we don't see? 1 minus 1/k. So if I wanted to see person 4, They would have to be the tallest of the first 4 people. And since we're assuming all orderings are equally likely, it doesn't matter what's going on beyond that. All that matters is of the first 4 people, what's the probability the largest of the first 4 is in slot 4? So it'll just be 1/4. Okay, we haven't done the calculation yet, but now that we see 1, 1/2, 1/3, 1/4, let's go back to our board of guesses for like a game show host. Which one would you like to choose now? Why do you want to choose the log? Yeah, it's looking like a harmonic series. So the question is, are we surprised that the answer is around log n? It means we're seeing a lot of people, not just a constant number. So as n gets larger and larger and larger, we see more people. Does that seem reasonable? Yeah, because I can always just look at the first n people. I see some number of them. And then if I put down another block of n, in some sense it's almost like independent, and I should be able to see a little bit more. I'd expect to see some more people from that. But a really tall person in the beginning can kill seeing a whole number of people afterwards. For instance, once you hit the tallest person, you can't see anything past them. And so what's the probability the tallest person is in the first half? 1/2. So probably not going to be too close to n. And you could look at, what if I see one of the tallest 5 people? What's probably one of the tallest 5 people is in the first quarter, or something like that. And you can probably get a really high probability that you have a very tall person. Or maybe, what's the probability that none of the top 10% of the people are in the first 20%? It should be extremely unlikely. And so you should be able to keep whittling that constant down. So probably a constant times n doesn't make sense. Harder to deal with square root and n to the delta. But it seems reasonable that it's not going to be as high as this. And now as soon as we start to see these fractions, now the logarithm is looking appropriate. And so the number of people we see is just whether or not we see the first person all the way down to whether or not we see the last person. And now we just do linearity of expectation. The expected value of Sn is the expected value of x1 plus the expected value of xn. So for the expected value, it's going to be 1 times the probability it happens plus 0 times the probability it doesn't happen. Well, since this is a 0, I really don't need to calculate the probability it doesn't happen. So the expected value is just 1 times 1 over k. So the expected value of xk is 1 times 1 over k plus 0 times 1 minus 1 over k is just 1 over k. So this is going to be 1 plus 1/2 plus 1 over n, and that's approximately log of n. So it's a nice example. What was done on Wednesday was we saw the harmonic series coming into play with the egg drop problem. We saw expectation coming in. So I thought it would be a little bit fun to talk about this problem here. Now, the question is, how do you prove this? Do you remember the integral test from calculus? When you take a sum that's monotone increasing or decreasing, you can approximate it with an integral. Who forgets that and would benefit from seeing it? Okay, all right, so let's do that. The other thing is, the harmonic sum is just such a wonderful sum. I'm going to give a short proof that it diverges. Does anybody know a non-calculus proof that the harmonic sum diverges?
I think I made one, but I'm not sure if it's completely accurate or if I completely remember it.
Okay.
I remember one.
How do you do it?
Say h equals 1 plus half plus a third.
Uh-huh.
And you show that h is larger than 1 plus a half plus a third. 1 plus 1/4.
Good, yep. Excellent. So here's the harmonic sum. This is less than or equal to 1. plus 1/2. And then I'll put these two terms together. Oh, I'm sorry. Greater than or equal to 1/4 plus 1/4. And then I'll put these next four terms together. 1/8 plus 1/8 plus 1/8 plus 1/8. Right? Each one of these now sums to 1/2. And so this would be greater than or equal to 1 plus 1/2 plus 1/2 plus 1/2. And that's not too bad to show that it diverges. Now this is giving us a lower bound. If I wanted an upper bound, could I get an upper bound without too much trouble?
An upper bound on the first n?
Yeah.
I mean n.
So if I replace 1/3 with 1/2, that will be an upper bound.
You just shift the.
I basically just want to shift the parentheses. And then if I take 1/4 plus 1/5 and replace that with 1/4 plus 1/4, and then I do 1/6, 1/7, 1/8, 1/9, and replace it with 1/8, 1/8, 1/8, 1/8. What that's telling us is that I'm going to be within about 1, 1.5 of the correct answer. So the upper bound, it should be less than or equal to 1 plus 1/2 plus 1/2 plus 1/4 plus 1/4. So without even using calculus, we can get a pretty good approximation. So let's say we go 1 plus 1/2. What do we want to stop at? What term? Yeah, we definitely want to stop at 2 to the n plus 1 over 2 to the n. And this will be approximately 1 plus 1/2 plus 1/4 plus 1/4 is 1/2. So about how many terms do we have?
Maybe we should have 1 over 2 to the n minus 1.
So, I mean, this is the issue now in terms of exactly how many terms. So we have 1/2 about n times. Yeah, we're within 1 or 2 of it. So this sum should be approximately n over 2. And then what is n? So if this is our whole number here, this is approximately the log, let's let n equal 2 to the n of n base 2 over 2. So as a rough ballpark. And then the question is, can you make this a little bit more precise? It's supposed to be the log of the number. We're not supposed to have it base 2. We're supposed to have it base e. Can you fix everything? But as a really quick rough estimate, it is giving us upper and lower bounds of size log n. You know, it's pretty nice. All right, so we'll do the integral test quickly, and then we will end the semester with the strategy game. I can prove a winning strategy exists. I do not know what it is. And maybe I'll also mention, yet another fun game of tic-tac-toe that's possible to play. Yet another variant. So when you have the harmonic series, here's 1, 2, 3, n. And I want to calculate the sum. One thing I can do is I can write the sums like this. Here's 1, here's 1/2, here's 1/3. Not to scale, here's 1 over n. If I now draw the function 1 over x, then the area under this curve is going to be greater than the sum. And then I unfortunately have this one extra term over here. So I'd get 1 plus 1/2 plus 1 over n will be less than or equal to 1 plus the integral from 2 to n of 1 over x dx. And so that will get us an upper bound of, this will be 1 plus the log of n minus the log of 2. Yes?
Why are you integrating from
I should be integrating from 1, thank you. Good. And I don't even have to worry now about the log of 2. Excellent. All right, now if I want a lower bound, all I need to do now is I have my sums going in the other direction, going from 1 to 2, and this will go from now n to n plus 1. And so this should be greater than or equal to the integral from 1 to n plus 1 of 1 over x dx. And this should then become the log of n plus 1. And the log of n plus 1 is the log of n plus the log of 1 plus 1 over n. This is approximate of size 1 over n. And so that gets you very quickly that the area under the curve is about log n. So this is called the integral test. It works so long as your sum is monotone, either always going up or always going down. You can do better approximations in this. There's the, it's Euler someone. When in doubt, guess Euler or Gauss. But there is a finite summation formula that does a better job, estimates how much things are off by. As a nice aside, how could we use this to estimate the log of, crap. I wrote log. I didn't mean to write log. I meant to write, how can we use this to estimate the size of n factorial? But I have trained myself so well that even when I see a product, I cannot help but write log. And so the punchline has been sadly given away, right? Well, when you see a product, you take a log. The log of n factorial is now the log of 1 plus the log of n. We can now apply the integral test. This is going to be approximately the integral from 1 to n of the log of x dx. Does anybody know the best way to find the antiderivative of the log of x?
integration by parts?
What would you integrate by parts?
1 times log of x.
So when you integrate 1, does 1 go up to x?
Yeah.
Okay, so let's try that. So we'll let u equal 1. dv is the log of x.
dv is 1.
Okay, dv is 1. Okay, and then u is the log of x. All right, so du is going to be 1 over x. v is going to be x. That's going to work out. And so you will get that this is equal to x log x minus x. And then we just evaluate this at 1 and n, and you get approximately n log n minus n for n factorial. I'm sorry, for the log of n factorial. So n factorial is about e to the n log n minus n, which is n to the n e to the minus n. If you remember Stirling, that's pretty much the beginning. Now Stirling also has a factor of square root of 2 pi n. If you think about what we're missing, the first term and the last term, the first term is of size log 1. The last term is of size log n. The average is 1/2 log n. 1/2 log n is n to the 1/2. Log of n to the 1/2. And when you exponentiate log of n to the 1/2, you get square root of n. So what we need is a slightly refined version of integration of the integral test to actually figure out what do we expect our error to be. And I will actually give you the square root of n over there. It's a powerful technique. It's worth knowing this. It's a great way to estimate these things. The other way to do this is the method of divine inspiration, which is to just write down the answer. And this is not an unreasonable thing to guess. You could just try guessing x log x. Because when you take the derivative of x log x, derivative of x is 1 and you get a log x, which is great. And then when you take the derivative of log x, you get 1 over x, so you get a 1. So you're off by 1 when you integrate. So what we need to do is then we need to subtract the 1. And so you start off with a guess and you refine it. Okay. Any other questions on harmonic series, integration by parts, the wonderful techniques? All right, so I'm going to say the final version of TicTacToe that I've looked up and is fun to play. So you start off with a very large grid. That should be enough. Right. And the first, if you want, you can assume it's an infinite by infinite grid, and the first person goes. If it's an infinite by infinite grid, where does the first person go? In the middle, right? Without loss of time, they go in the middle. And the way the game works is the following. On your turn, you must play legally in a 3x3 tic-tac-toe board, but the board can be invisible. So whenever you put down a piece, it must have been such that there could be an invisible 3x3 tic-tac-toe board. Could I go all the way down here? No. I could go as far away over here. I can go as far away over here. So I would be, on my next turn, in something like this. This could be in the center. It could be bottom right, bottom left, top right, top left. And I can go anywhere in this. So really, you only need a 5x5 board. And the first person starts in the middle. And now the second person goes. And based on where they go, the next person has to go in such a way that it would stay a legal tic-tac-toe game. And you keep going, so it has to be legal at all moments in time. And first one to get 3 in a row wins. So what do you think person 2 would try to do now? So if you go 2 spaces away, you have then fixed which half the board must be on. But this could still be the middle row, the top row. So for instance, if I go over here, where do you think player 1 would go? Well, if player 1 now goes over here, where does player 2 have? That now fixes the board as this. Where does player 2 have to go? I'm sorry? And player 1 wins. Player 2 has to go here, and then player 1 goes over there. So if you go 2 over, it's a loss. 1 down, how many moves to go? How many possible moves are there?
You have to stay within the 3x3 whatever frame.
Correct.
Until you fill it up.
Well, until you could, as long as you can justify to somebody, hey, there was an invisible frame down, and this is where it's located. My move is legal. As long as you can justify that, you can move wherever you want. So, for instance, if I move here on your turn, you could not move there, because I can't put down a 3x3 frame. But you could, if you wanted, move up over here. If you go there, that's also enough for a win, because that forces, and you can go like that. So there's lots of ways player 1 could win if you go 2 over. So how many possible moves are there for player 2 to respond? What are the 5? So this was definitely 1.
Then there's the one immediately to the right of 1.
2.
And then the 2 below 1 and 2.
So right here,
Yeah.
3,
And then,
4.
And then under 3.
Yep. Because by symmetry, these are all going to be 5s. These are all going to be 3s.
How do we justify 3?
Over here? Oh no, I'm just saying that this is a different type of move.
Oh,
If player 1 goes here, player 2 goes here, that's different than player 1 goes here.
okay.
And then just by symmetry in terms of rotating the board, so 2, 2, 2, 4, 4, 4, and then this is the same as a 1. And we've already shown that this is a bad place for player 2 to go. So we can eliminate that.
I mean, 2 is always bad, right? 2 is bad in normal TicTacToe.
Okay, so if you go here normal, so would that be enough to kill you? Yes, because, well,
So you could just do the normal TicTacToe.
all right, so let's see if that would work. All right, so we start off X, O, and then a normal tic-tac-toe. Let's see, if you go here,
And you have to block, and then you have to.
Well,
we've got to be
you don't
careful.
have to block. You can go in the row above.
If player 2 goes over here now, you can't do that 3 in a row. Right. Now, if player 2 goes here, you go here and you win. But this is where the game gets interesting. The board hasn't been determined at this point. If you go here, if player 2 goes here, you can no longer get 3 in a row by going there.
So player 2 has to go there.
I'm sorry?
But wouldn't that be, that's the only move that player 2 can make?
What, going here?
No, going in the bottom left.
Well, what if you go over here? Or what if you go over here? So you have a move here or here. You could even go all the way up over here. Now again, that would lead to a loss, but I'm just saying there's more things to analyze because you don't know where the board is. So there's not that many cases. I'm sure this is online, but if you're looking for other variants of tic-tac-toe to play with little kids, this is where you can beat the crap out of them. You can do the mathematics. And it's interesting to see how many twists are there on a game that you've known since childhood. How many of these versions of tic-tac-toe have you ever seen in your life? And this is one of the themes of the class. Whatever you're doing, ask about generalizations. Ask, how can I push this? What new things can I do? Okay, so the last thing I wanted to do to end the semester on is the n by n grid game. So in a lot of these games, it's whoever does the final thing wins or loses. If eat last piece and lose. You have a n by m board. On a turn, you eat all x, y, such that x is greater than or equal to I, y is greater than or equal to j. So you basically choose a rectangle in the upper right corner of the board. So imagine here is either 4 by 5 or 5 by 4 board. If I choose here, I eat these 4 pieces. If I choose here, I eat those 6 pieces. What if you win if you eat the last piece? What would player 1's strategy be? Yeah, bottom left. The game's kind of boring, right? So clearly we want this game to be whoever eats the last piece loses. Where does player 1 definitely not want to go? Bottom left? Okay, good. Bottom left is probably the worst place for player 1 to go. What other square would be really bad for player 1 to go? So this is an immediate loss. Yeah, to the right of it or right above it. Because if you go here, you eat all these pieces, and now there's just this one row. Player 2 goes right above and forces you to lose. Anybody ever see the movie Laser Team? There's a reason. My kids and I just watched this. It actually describes it as your 4 complete losers must save the planet. And we were shocked that it actually describes them as losers in the description. But if you go here, this is bad. If you go here, it's almost as bad. Now, I can have any size board. What kind of constraints do you want to assume about m and n? I mean, you might want to be able to play on a square board. But there's one constraint that you really want to assume about both m and n. Okay, well, So that would be interesting. What if they're not finite? What if you looked at the infinite version of the game? So we'll assume finite. I like finite. What else might you want to assume about their size? Greater than 1. If one of them was just 1, so you start off with a column, it's not a really good game for player 2. How many of you have ever played Connect 4? Okay, so some people have never played Connect 4. You have a bunch of circles and you drop them, and it's like a grid. And if you drop something on top of another piece, your piece gets higher. And the goal is to get 4 pieces of your color in a row, or in a column, or diagonally. How many of you have ever played Connect 2? So Connect 2, the second person always loses. We want to at least give both players a fighting chance. Whether or not both players actually have a fighting chance is another story. The game needs to at least look fair. So one of the things you learn as a math professor is when you're when you're designing games to play with your students or children, it has to look like they have a chance. And you go, what if so would you rather be player 1 or player 2? What do you think? Do you want to go first or second? Who has does someone have a winning strategy, or does it depend on M and N? So you can gather data, right? You can play lots and lots of games. But there's so many possibilities. How many opening moves do you have?
Every single square is
Yeah, so you have m times n possible opening moves.
You can divide by 2 for symmetry.
Can you?
Well,
No.
depends on the board.
No,
Depends on the board.
because you kill everything above and to the right. So you don't have complete symmetry. So you have m times n possible opening moves. And depending on where you go, there's a lot of possible responses. So the analysis gets quite involved.
Does it depend on whether or not M and N are odd or even?
So it seems reasonable that it could depend on parity, it could depend on number of points. Given that we have about 5 minutes left in the semester, this is a great time for divine inspiration. Right? Give me a good place, give me a possible place for person 1 to go. Upper corner. Great choice. If you want to think about special points, the upper corner is the most special. So there are 2 possibilities. Player 1 has a winning strategy if they go in the upper corner, or they don't. And if they don't, who has a winning strategy? Player 2. Okay? We are assuming that these 2 people are mathematicians. Or maybe a mathematician and a statistician. The major's getting a little bit better. Okay? Let's assume player 1 has a winning strategy. What should player do from this point onward?
If player 1 has a winning strategy?
Yeah, by going there. What should player 1 do from this point onward?
Just always going.
If they have a winning strategy, what should they do from this point onward?
Win.
Well, no, they take the top corner. And let's assume that player 1 has a winning strategy if they start in the top corner. What should they do from this point onward? Continue, right? Case 1, top corner. Follow winning strategy. Okay? If there's a winning strategy, follow it. Case 2, they move in the top corner. So we'll say top corner is winning. In case 2, top corner is losing. What should player do from this point onward?
Player 2 should win now.
So player 2 should win now. So what should player 2 be doing?
Well, player 2 is
Yes.
Player 2 now has a winning strategy. Player 1 had the winning.
Correct. Let's say player 2 has a, so player 2 now has a winning strategy. Let's say that winning strategy is to go here. And that's where player 2 goes. Well, no matter where they go, they're going to kill this upper right corner. So player 1 says, oh, well, actually, I didn't mean to go there. If the top corner is losing, change to player 2's winning strategy. And now, this is player 1's first move. We have just proved, I mean, in some sense, this is the way to end the semester. I almost wish I could have, no, I won't say that. We have just done pure mathematics at its greatest. We have shown the existence of a solution with no idea at all how to find it. Yeah. This reminds me of a joke of a plane that's flying. All the instruments break down. It's extremely cloudy. They don't know where they are. They don't know where the runway is. They see the outlines of a building, and as they fly by, they roll down the window and says, where are we? And they hear the response, you're in an airplane. The pilot then banks, does these incredible flips and flops, and lands perfectly on the runway while the co-pilot is just going like this. He goes, how were you able to land the plane so perfectly and accurately? Well, the answer we got was immediate, it was accurate, and provided no useful information to the problem at hand. I knew that was the mathematics tower. And so, if you look at this, we have shown player 1 has a winning strategy. Do you have any idea what that winning strategy is? No. Should you even go in the upper right corner? We don't know. So there may actually be a winning strategy that has been done for this problem. I don't know. But I just love the fact that we can prove that we have a solution. And this is, I think, one of the best examples I know of the dangers of existence proofs. Just because you know something exists. It's nice to know the object exists, but frequently you want to be able to find it. So it has been a fun semester. Have a great time with the rest of your finals, especially if you haven't finished this one. If you have done your finals, they're already graded if they were handed in before 8:45 a.m. today. And have a great one.